talk by engineers for engineers. And this week I have with me Piyush Jain, who's looked into quite a bit of isolation levels, transaction retry semantics, failure semantics of transactions, all of the cool deep stuff that no one thinks about but always takes for granted. So we'll kick off in a minute or so. Once again, welcome folks, and if you have any questions, feel free to ask it directly on the LinkedIn comment box or join our community Slack, yugabyte.com/Slack. You can ask it there, and we can get started. Hey, Piyush, thanks for joining us. Where are you located? Maybe say a couple of things. We'll get started in a minute.
I see. So a warm welcome to all as well. I'm in Sunnyvale, where our office is. Yeah.
Awesome. Awesome. Fantastic. In office.
Yeah.
Yeah. And that's probably a virtual background, but it's still the office, right? So real office with a virtual background. So got it. Fantastic. Okay. So maybe we can just get started. All right. So once again, folks, welcome to our weekly Yugabyte Friday Tech Talks. This week's topic is high availability of transactions. Piyush, why don't you give people a little bit of like in a minute, introduce yourself, your background, what you worked on, and then we can get this show and tell us what you have with high availability of transactions.
Okay. So as I said, I'm located in Sunnyvale. I've been with Yugabyte for 2.5+ years, I guess. Have been working on a lot of the transactional semantics stuff, mainly trying to get the semantics of Yugabyte to be as close or matching with Postgres semantics, right, in terms of transactions. And this goes down to the very deepest of things, wherein if I were to give you Yugabyte and Postgres and run a workload, you wouldn't be able to say which one is which if they were behind a black box, right? So that's the level of detail we have been working on to get it to exactly match, while also respecting performance and keeping it distributed and correct. So it's a complex, hard problem to solve, but I feel that we are very close, right? And in some cases even better than Postgres, I must say. But yeah.
Awesome. Fantastic. Okay. Can't wait to hear how. Anyway, it reminds me of the Turing test where you have to ask some questions and say whether it's a robot or a person. And in this case, you can't really tell if it's Postgres or YugabyteDB. So why don't you kick us off? What do you have for us on this topic?
Yeah. So today we'll discuss HA of transactions, that is high availability. And what this is more important in the distributed context. So let me go to the first slide, right? So we can have node failures in a distributed system, right? So we want failovers to be seamless, in the sense the user shouldn't worry about nodes failing. That's the whole purpose of, one of the big purposes of Yugabyte, right? So we'll discuss that. I will even demo wherein node fails while a transaction is running, etc. So we'll discuss that HA part, which Yugabyte handles internally. And then coming to the next 3 points, right? So when you use, for example, read committed isolation, right? So actually, taking a step back, when you use transactions, you inherently have serialization errors, right? If there is contention. Now, it's usually the application's duty to retry these errors. Now, Postgres provides read committed isolation, wherein it automatically handles serialization errors internally. The client doesn't have to worry about these, retry these, etc., etc. And most of the people in the community or even in industry have been using read committed because it's the default in Postgres. So a few months, I don't know, like few quarters before, we introduced this isolation in Yugabyte as well. And we give the same guarantee. That is, you don't have to retry serialization errors, don't have to worry about it, right? Just keep your app simple. After that, we'll discuss other isolation levels which do require retries, even theoretically. There's no way you can handle them because they give stricter guarantees, right? Like repeatable read and serializable. So we'll talk about some best effort retries we have done even there, right? Postgres doesn't have them actually, but we do because it's a net benefit gain without messing around with the semantics. So that's point 3. And then fourth, even after all this, you might see serialization errors in the other two isolation levels, right? So what can you do as an app developer to ensure that the app is resilient and you don't have to throw the error back to the user? So that's 4. So yeah, this is what is the agenda. Yeah.
Fantastic. All right, let's get underway.
Okay, let's dive in. So I mean, first we'll discuss how Yugabyte handles node failures when you have a transaction going on. So for this, let's see the flow of a transaction, right? So let's assume a client is issuing a simple transaction wherein begin to update statements and commit, right? So the client connects to some node which has the YSQL. Let's assume we are in YSQL land, right? Postgres. So it connects to some backend, which is a transaction manager. So it coordinates all the stuff across the cluster, like issuing writes, creating transaction, etc. Now there's another node, actually a Raft group, which stores all your transaction information, like is the transaction running now, is it committed, when did it start, etc., etc. That's your status tablet. Not really important for now, but just mentioning that this is something we store somewhere. Could be some other node, and this is also Raft consensus backed, right? And then there's few shards wherein you might be writing data, right? So for example, key 1 might be on tablet server 3, key 2 might be on tablet server 4. Now both of these are inherently Raft backed as well. So what happens during a transaction is you write to different shards of data, and then you finally commit the transaction, which involves two-phase commit, etc., etc. I'll not go into those details. What's of more concern to us now is, given this system, what if we have a node failure on, let's say, the one hosting data? How does Yugabyte handle this? So since this is Raft backed, there'll be a leader failover seamlessly occurring. The client doesn't know there's a failure, right? The transaction doesn't know about it, and the previous writes would still be visible, as well as any new writes would come to the new leader, right?
Got it. So the scenario we are looking at is we are going to do a distributed client-driven transaction. So which is begin, and then we'll do a few statements and then commit. And we are going to do a few statements, and then we are going to go to the node which owns the row that we are updating. And we're going to kill that guy. And we're going to see if the transaction can continue or not.
Yes.
Okay. And as in, we're going to see that it can continue. Okay. Sounds good. Let's do it.
Let me show that actually, right?
Okay, let's see it. Let's see it.
So,
Awesome.
I actually have a cluster running just to save time, right? So I created a cluster, 3-node cluster. And if you see, so there are 3 zones actually, right? 1 node in each zone. Is the font fine? Let me zoom
Yeah, a
in.
little bigger. Yeah, that is better. Yes.
So there's 1 node in each zone, and I have kept node 2 as the leader for all data. So I used table spaces, which basically allows you to pin tablet leaders to some node, right? For various reasons. So I just pinned everything to this node, which means all your data. You're on mute, Karthik.
So yeah. So the row will be written to the second node. That's what you're trying to say, correct?
Yes,
okay.
yes.
So when you perform the transaction, you are connecting to the first node, and you are going to write a row which will acquire to do a provisional write. It's not a visible write. It's as a part of a transaction to the second node. And then halfway through this, you're going to kill the node.
Yes.
Okay. Sounds good.
And yeah, that's right. So let's do that actually. So let me connect to, so I've just kept the IPs 1, 2, 3.
You mind making the font a little bigger?
Oh yeah.
Yeah.
Is that better?
That's fantastic. Yeah.
Yeah. So I connected to node 1. So we have some data here, right? Now, if I begin a transaction, all nodes are up, right?
Yeah.
I begin a transaction. Let's say I update test set v equals 10, where k equals 1. So we did an update. It is visible to this transaction because it is still provisional. I mean, this transaction can see it. Now let me stop the second node.
Could you? Yeah. Fantastic.
Let me increase the font. So I'll be stopping the second node, right?
Okay.
So I have stopped it. Now, if you see here,
Yeah.
rebalancing is occurring. One tablet has already
Yep.
moved here.
Yep.
All three have moved. So all the data is now on node 1. Now, if I do select star again, you can see the 10, which was provisional. Let
Even
me
though
do
the node to which you had written it had failed, you can see it because it's replicated and available.
Yes, exactly.
Okay. And what happens if you do this from outside? Like, let's say you connect to like the same cluster from a different shell and you do a select star, will it show the 10 or not? Like, because this should not be visible to anything other than this particular transaction.
Yeah, it won't show the 10 because it's not visible yet, right? It's not committed. So, for example, I connect to node 3.
Okay.
Right? Select star from test. So you still see 5.
Perfect. Yeah. Perfect.
Now, if you commit, I mean, not commit, but let's say I update key 2 as well.
Okay.
This is after the failure. So now the data has been written to node 1, really. Right?
Yeah.
Now, if you do select star, both are 10.
Okay.
Now, let's do one thing.
And let's try it in the session outside just to make sure nothing has changed there at all.
Yeah, nothing has
changed. Still private to the transaction so far. Got it. Even after a failure happening through the transaction, etc.
Yes.
Got it. Okay.
Now there are two options I give you. Either I commit now and then start the node, or I start this node and then commit. Both work in Yugabyte. So, I mean, it doesn't really matter.
Doesn't matter. Let's commit. Yeah, let's commit. Wow, that's choices. Okay, now it's visible everywhere. Yes.
Yeah. The only difference if I committed later was that the data would again move back to this leader.
Yeah.
For example, if I start, because that's the leader preference I have given, right? Using
Got it. So you're forcing that to be the leader if it's up. It's up. Yeah.
Exactly. So again, the balancing has happened and we are good here. So, I mean, this is how the failure is handled. Now, I could even run a YSQL bench workload and really show the TPS decreasing, going to 0 and increasing again. But I guess I'll skip that in the interest of time. But if it's interesting, I can do that.
Now we'll come back to it. Yeah, we'll come back.
Okay, we'll come back. So let's go back here. Okay, so we saw that if a node fails, we do it seamlessly. There's no split brain scenario because of Raft, etc. The same thing would happen if the node or the Raft group really hosting the tablet status, like metadata fails. So that is also seamlessly handled.
Yeah.
Now, coming to this scenario, what if the node which the client has connected to fails? So as of today, we don't really handle this because the backend is not really Raft consensus backed, and there's no real, I mean, we didn't really find a good
way to do it, right? There's no real way to do it though, right? Because it is a transient thing on the client side, correct?
Yes, exactly. There's no real way to do it as well. I mean, there could be some ways to do it, complex ways, but that would, involve additional app complexity.
Yeah.
I mean, but that is a no-brainer, I guess. So changing apps is hard.
Yeah.
So that was that. The 3 failure modes. Now, quickly, I'll just touch this slide. So when you do this high availability, right, in a distributed database, it's not just Raft which helps, right? It's not like you put in Raft and okay, magically you get this. There's a lot of work which goes in. For example, so this diagram right here, right? This YB client is basically same as the backend here. Okay. So your query layer, if it like issues write operations, etc. to T server, and let's assume this case wherein the operation was completed, but because of distribution and async RPCs, right, you don't get back the response. So the query layer thinks it's timed out and it retries the request internally, right? Now, this can result in duplication of a write, etc., etc. So we need to handle such cases as well and ensure that they go well with the Raft consensus algorithm. So this also has to be Raft backed, right? We don't want split brain scenarios to result in double counting problems or extra data being written. Yeah,
correct.
So that's that. It's a sort of complex problem, really. Another thing, like this failover stuff, right? whenever you do a rolling upgrade, you actually access this path. So it's not like this is the non-happy path.
Yeah, rolling upgrade, or you want to change machine type, lot of such inherent things where, yeah, makes sense.
Yeah.
Makes sense.
So it gives more confidence that when an actual disaster occurs, it'll be safe because your cluster has already been through it, right? Many times.
Yes.
This as well, right? Any feature we think of, we have to think of this HA. Like this was the basic tenant, right? So tablet splitting was a major feature, wherein you automatically shard tablets when they grow large, and you don't want to abort any transactions touching those tablets. So you create child tablets, but you still ensure everything is running smoothly, right? So hard problems, I just want to say, yeah.
Makes sense. Makes total sense. Yeah. Okay.
And,
Yeah. What else do we have?
okay, let's move on. So, okay, let's discuss serialization errors, right? So this was HA of transactions handled by YugabyteDB. Now there are okay, pausing there. What are serialization errors? So when you have transactions running in any isolation, right? If there's a lot of contention, they might be touching same pieces of data. Now you have, like, when you touch the same piece of data, there can be correctness violations, in the sense unintuitive things can occur. So to guard against this, databases created the concept of isolation levels, right? And different isolation levels give you different semantics, right? Some are like really strong, like serializable. They give you the most intuitive behavior. Like even if you don't know what isolation means, serialization gives you the intuitive behavior. You don't have to worry about anything. And then there's the weakest, which is read committed, which gives you unintuitive behavior, but it does something wherein you don't have to worry about serialization errors, right? Which can occur in the most intuitive one, which is serializable isolation, let's say, or in the middle one, which is repeatable read, right? So what I really want to say is, when an application is really issuing transactions for any sort of work, uh, if they use read committed isolation, they don't have to really worry about retries of serialization errors. The database is going to handle it internally, right? Postgres does it that way, and we do the same, right? So,
So serialization, the isolation levels are often a very complex topic, right? So for people who are viewing and who are more app developers, generally what I hear is, I don't really care. Tell me what I should use and just make it easy, right? So in this particular case, just want to say, like, I know you're saying read committed, repeatable read, serializable, and different levels of semantics. What does Postgres do? Because a lot of people are used to using Postgres, and a lot of frameworks are using Postgres. And so people know how to make it work for Postgres as opposed to learning this. And if they want, they can go figure it out for Postgres. What does Postgres do? What does YugabyteDB do?
So let's start Postgres, and it'll be easy to explain, right?
Okay, let's do that.
I have with me, let me increase the font. 2 Postgres sessions, right?
Okay, this is all Postgres now, no Yugabyte, right here.
Not Yugabyte, and this is PG15, by the way.
Okay.
So I have a simple table. K is the primary key, right? And if you see, there's 2 rows. Now in Postgres, let's start with repeatable read, right? The reason being, that is snapshot isolation. I think people would be familiar with it. So let me do repeatable read, and let me do the same here as well, right? So 2 repeatable read transactions. Now what I do is, I update test set v equals 5, where k equals 1.
Okay.
Oops.
Typo.
Yeah. So I did this update. Now if I do the same update, or I mean, let me just change the value at least.
Yeah.
So we have this behavior wherein the second transaction is going to wait for the first one in anticipation that if this guy rolls back, I will make progress, right? They're touching the same piece of data. But if this guy commits, what does Postgres do? It just could not serialize access due to concurrent update. So this
because
is
repeatable read says that you cannot update an already updated value. in the
Yes.
middle of a transaction. Write conflict, right? Okay, got it. Okay.
And since we are here, let's also see what read committed does. So read committed is the default, so I don't have to give any isolation level. So I say begin update, blah, 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 and then let's say 15. Okay. Now, same thing, if I do here, and let's make it 20, right? So the same waiting still happens, right? You can see the waiting. Now, if you commit, this guy doesn't error out, it makes progress. So what read committed does is it really retries whatever is conflicting on a new snapshot.
Read whatever is committed, right? Like,
Yeah, read whatever is committed.
Makes sense. Yeah.
And now if you see the latest value, I mean, the one which came later got written. So that's basically read committed. It's a very coarse way of just retrying stuff to avoid serialization errors, right?
Yeah, because in the other case, there's nothing a database can do. Your application has to say, yeah, but that's okay. Why don't you go and update it anyway, even if it changed, by reissuing the same sequence of statements?
Yes.
And if you have, 10 such statements or 20 such statements in parallel, you're in trouble, right? Because you'll have to keep reissuing the same statement until your version of it gets through.
Yes, exactly.
Makes sense. Yeah, makes sense. A lot of real world scenarios where read committed is useful, I guess, and that's why it's the default. Yeah.
Default. So this was Postgres basically. Now let's try the same on Yugabyte, right? So did I start my node again? Doesn't matter actually, but
it doesn't matter. I think you did, but yeah.
Okay. So I have the same, I mean, similar table. Now, if I do begin transaction, isolation level, repeatable read, right? Let's do the same here. The thing I want to show is update test set v equals, let's say 5, where k equals 1. Now, in repeatable read, if the other guy is doing, let's say 25 or let's say 0, right? We have the same waiting behavior as Postgres. Now, if I commit, this guy makes progress. This is unlike Postgres. Now, if you see, the value is 0, the latest one. Now, you might ask me, are we violating repeatable read semantics in any way? Like, will you see all the unintuitive behavior, like intricate isolation level stuff? So the answer is no, we are not violating any semantics. So what happened here is the update knows that it's conflicting. Now, after this guy commits, Postgres tries to do the update, sees there's a conflict and just errors out. In Yugabyte, we know that no data had been sent to the client back, right? So this was the first statement. So Yugabyte acts smart and just restarts the whole transaction, right? Because
what if you had read the row before you did the update?
Oh, then you would have to throw a conflict error because
Can
you
we
don't
try that? Yeah, can we do the same
Yeah.
thing? And okay,
Let's,
cool. Goody, we're going off the script. This is fantastic. So
Yeah. No, I wanted to show this actually. Good point. So if you, let's say, do something like this, and let's assume the app was putting a
now
value.
deciding based on the value what you want to do. Yeah. Okay. Got it.
Exactly. Let's say it was 0 plus something, or I don't know, something based on 0. Nothing
Okay.
can happen on 0 really, but fine. So if you see this now, it says could not.
Fantastic.
Yeah, that makes sense, right?
This is really narrowing the window of retries to make sure, even going above and beyond Postgres, to figure out where it violates, where it doesn't, and
Yes.
still maintain semantics, but fantastic. This is really awesome. Yeah.
Yeah.
So
So
I hope the viewers are feeling as excited as I am. So anyways, let's keep going.
yeah, so this is what the real point, right? Wanted to highlight. Postgres 15 doesn't really have best effort retries. I think they can. It's not really hard, I think.
Yeah.
But it's just hard to add it in such a complex code base, right? Actually, we did because we use PG as well. So anyway, now the other thing I wanted to mention is, sorry, let me go back. I can
And by the way, in YugabyteDB, if you do read committed, I'm guessing the semantics are the same as Postgres, no difference, correct?
Yes, the
Okay.
semantics
Yeah,
are
no
the
need to
same.
show, but it's just going to be the same. There's no difference to that. Yeah, makes
Yeah.
sense. Let's keep going. Yeah.
Now there's, one other thing I could show, which is I had this. So YSQL bench allows you to run a lot of concurrent workload easily.
This is
So
like PG bench, right? This is
yeah,
basically.
this is exactly like PG bench. Yeah. So for example, in read committed, now the same situation we spoke about right now, correct? Which is this one, if you run concurrently, it's just incrementing, but after a select. So
Yeah.
this should not be able to retrain repeatable read.
Yes.
It would boil it.
Yeah.
But in read committed, it does go through seamlessly, because so if you see there's no errors. Actually, let me show the okay, let's do this. No, let's do this. Let me just set the value to 0. Right? It's just increments, right? So we'll see if it incremented 200 times, right? Or let's make it 4. Let's increase the concurrency, right?
Okay.
So, there's contention. It took some more time. It ran. Now, if you see, it should be 400, right? So all 400 increments ran without any errors, right?
Yeah.
Now, let me just show this with repeatable read, actually, because
now you cannot do a select followed by an increment, so you're in trouble. Yeah.
Yes. Now you can't do a select followed by an increment. So if I were to run the same in repeatable read, so remember the counter was 400, right?
Yeah.
So this was the file. You see some errors, right? So there are best effort retries, but they don't work here because of the select.
Yeah.
You see the errors. Where are the errors? Yeah, 57%. Roughly half of them fail, right? So if you see the count, it would be not 800, but something lower.
Much less. Yeah. Makes total sense. Yeah. This is a very clean example, very easy way to demo the power of read committed. Yeah. Makes sense.
Committed. So yeah, that's the power. Now, you might be in a situation as an app developer, a lot of legacy code with, let's say, repeatable read isolation, right? Now, you still get these conflicts even after the best effort retries, because theoretically you can't do anything really. That's isolation level theory, right?
Yeah.
So what do you do then, right? What do you do as an app application? So if you get a serialization error, so there's two cases. Let's see this first. If you get a serialization error, there's really nothing you can do but retry the whole transaction yourself instead of everything out, right? So just roll back the transaction and do it again. That's basically what you can do, and what you should do, actually. Also, you should have
same, whether it's YugabyteDB, Postgres, it doesn't matter. Some other database, it's always the same, right?
Yeah, it's always the same. There's no getting out of this. Yeah. So, but remember, if you do this, do ensure you have some exponential back off kind of mechanism, because you don't want a thundering herd problem, right? Like where all of them just go in together to retry stuff. So you'll just be loading the system and getting no output. So ensure you have this back off. And I just created a very simple example wherein I have this. I'm doing this infinite retries kind of thing, but there are 100 iterations and they all try to do this increment, right? So if I see an error, I just roll back and do it again. That's what happens. Now, if I just run this, you will be able to see the retries. So let's do client retry. So this was the file. If you see, there's some retries that happen, but you can handle it seamlessly, in the sense you don't really have to go back to the client, to the user immediately with the error, right? So yeah, just wanted to share this as a tool. I will pause here, but let me not pause. So the other case, right? So serialization error is something wherein you have to retry the whole transaction. There's no other way. But if, let's say, you have some semantic violation, some Postgres exception, like unique index violated or something. And if your application has some corrective alternative as per the business logic, you have the ability to just undo the partial work that might have been done by the failing statement and redo the corrective action. You don't really have to restart the whole transaction for this, right? So how do you do that? You create a save point like before the statement around which you want this sort of exception handling, and if an exception occurs, you just roll back. Just basic simple thing, right? So that's the other sort of thing to keep in
Fantastic.
mind. Yeah.
Yeah, fantastic. Awesome. Yeah, so that brings us to time. I didn't see many questions. I think, folks, if you have, I think this is a fantastic demo, first of all, fantastic demo for all the segments, right? So thanks a lot, Piyush. It was quite useful and exciting. Once again, I don't see many questions, but if folks have questions, please feel free to post it in the LinkedIn comment box even after the talk. That's fine. We'll be looking at it, or join our Slack. It shows on the screen, yugabyte.com/Slack. Once again, as Postgres, as Piyush said, Postgres and YugabyteDB, we're trying to make it like nearly interchangeable. You can't tell the difference, right? That's really our aim. I think Christoph Bösler said, Yugabyte, love your 30-minute tech talks. You're most welcome, Christoph. And this week's thanks goes to Piyush. He did most of the work anyway. So thank you for that. And once again, folks, yeah, please feel free to drop a note, say hello, ask a question, anything. We love the interaction. So, all right. Thank you, guys. Thank you, Piyush. Once again, thanks a lot. Really appreciate it. This was fantastic. See you guys next week, same place, same time, right? So, and or maybe in 2 weeks, I don't know. So, but anyway, so we have another such topic lined up. So thanks, folks. Okay, there's a question. We'll continue. We'll do it. Maybe we'll take a minute to answer. Will read committed isolation be default in the future? Jim asks.
Yes, that is the plan. In the sense, in future, we want it to be the default because that is one more step towards, making it interchangeable with Postgres.
Yeah.
People shouldn't.
Yeah. So there you guys have it from the man who's actually doing it. So, yeah. But anyway, so there's your answer, Jim. And Piet, Frank, a lot of people say thanks. I think most welcome. Ishwar says, if we have a big data set and have many high value transactions, how can we choose that particular high value? Which basis can we take? I think, Ishwar, perhaps better to take this to community Slack. It seems like a deeper question for your use case. So we can help you there. Okay. Thanks, folks. Thanks a lot. I think see you guys in like a couple of weeks.
Thanks, everyone.